Hello everyone. Today I'm going to talk about how to fit a logistic regression model in R. So if you want to fit a logistic regression model, your response variable should be a binary variable or a dichotomous variable. That means your response variable should have it should be a categorical variable which has two levels. So first I'm going to load the data set. So I'm going to use this option from import dataset and from text read R. Then I'm going to choose the path of my dataset, which is in documents. So this is data2. So I'm going to give the dataset name as data2 new here. So here you can see there's a problem with the column alignment of this dataset. So what I'm going to do is so basically if you have something like this, when you just have preview of the data, that means there's a problem with your delimiter. So here R has automatically identified as your delimiter in this file as comma, but seems the delimiter of this file is to be something else. So I think it's white space. So if I choose white space over here, then you can see, yes, now you can see these three columns has separated very clearly. Okay, so that's what I need to do. Then I'm going to choose import over here. Okay, so now you can see I have imported the dataset into R. Now in order to just have a look on your dataset, that means how your variables looks like, I'm going to use this str function. So inside this str function you can give the dataset name or the object that you have created using this data file. Okay, so I'm going to do that by just running this code like this. So here you can see that the dataset has three columns. The first one is x1, the second one is y1, and third one is x2. So this y1 is basically our response variable, and x1, x2 are predictor variables. So as you can remember, if you want to fit a logistic regression model, your response variable should be a categorical which has two levels. So but here in R they have identified that variable as an integer variable. So now I want to change the data type of this variable to categorical, and at the same time when I consider the initial data set, the variable type of this x2 is also a categorical or a factor variable. So I need to change the variable type of both two variables. So in order to do that, I'm going to use this factor function. So if you want to change the variable type of a particular variable to factor or to categorical, you can use this function called factor. So inside this factor you need to give the variable that you need to convert. So I need to convert this y1 variable and x2 variable to factors. So I'm going to run these two commands. So when I run these two commands, and if I run this str again, now you can see that the variable type of y1 and x2 has changed to factor. Okay, so now you can see this y1 has two levels and x2 has 3 levels. Okay. Alright, so and there's another important function in R that you can use, this contrast function. So using this contrast function you can check whether how R categorize the variables. So as an example, in y1, when you consider y1, there are 2 levels. So when you have a categorical variable which has 2 levels, so the basically what R is going to do is it will create dummy variables which is 1 level less than the number of levels that variable has. So as an example, this y1 has 2 levels, so R going to create one dummy variable which is which denote 0 and 1. So here you can see when you run this contrast function, you can see the 0th level has coded as 0 and the level 1 has coded 1. But if you consider this second variable which is x2, which has 3 levels, so are going to represent this x2 in terms of 2 dummy variables. So if you run this command, you can see it has created 2 dummy variables. So 0 0 means level 1, 1 0 means level 2, and 0 1 means level 3. So this function is useful to you if you want to identify how R categorize the data. Okay, so now I'm going to just fit the logistic regression model. So this logistic regression model is basically one of the members of the generalized linear model family. So in order to fit the logistic regression model, you should use this GLM function over here, and inside that first you need to specify your model. So one of my goals here is to check whether there is a significant interaction between the predictors. So in order to do such a case, you have to fit something called a full model and the reduced model. So the full model should contain all the variables that you are going to test, and the reduced model should exclude the thing that you are going to test. That means, as an example here, in this example I need to check whether the interaction term is significant. So the full model should be this one, logi f, which should contain the main effects with the interaction effects, and my reduced model is this one, logi r. So that model should only contain the main effects without the interaction effect. So I think if you want to just fit the main effects, you can use this plus sign. That means x1 plus x2 means you are just fitting the main effects. But if you represent this model like this, x1 star x2, that means you are going to fit both main effects and the interaction effects. Okay, so now I'm going to fit these two models. So first I'm going to run this code. So here first I have specified the model and the dataset name, and here the one important thing is that you need to specify the family as binomial, because since you are fitting logistic regression model, the link function should be logit function and the family should be binomial. So as an example, if you are going to fit something else like Poisson regression model, then here the family will be changed accordingly. Okay, so if I run this code and using this summary function, I can see the summary of our model like this. So here you can see the coefficients of the model, x1, So here I have fitted only the model that corresponding to the main effects. So this is the details about the main effects of x1, and as you can remember, x2 has 3 levels. So R has generated 2 dummy variables to represent x2. So this x2 which is represent the level 2, and this is x2 which represent the level 3, and these are the estimates of the value and the standard errors with the z-test statistic and the p-value. So you can see here this x1 and x2 which corresponding to the level 3 is significant, but x2 level which corresponding to level 2 is not significant. But as a rule of thumb, if you are fitting a model with dichomatous or binary variables, you should include all the levels of the variable with the main effects if it is significant. Okay, so that's why the model included this term. So when you are fitting the model, you should include this x2 which corresponding to level 2 as well, although it is not significant. So now I am going to fit the full model. So here I have defined the model using the star. So that means I am going to fit both main effects and the interaction effects, and all the other things are quite similar to our first model. Okay, so now I am going to do I am going to check whether this interaction term is significant. So in order to do that, I am going to fit the likelihood ratio test. So if you familiar with the partial f test in the linear regression, this likelihood ratio test is also the alternative for that in generalized linear model. So we are doing the same thing here like we did in partial f test. So first you need to call this library which is lm test. So you have to first call this library lm test from your packages, and after that you can use this LR test function in order to just run the logistic regression model. So inside here you need to specify the models that you are going to compare. Okay, so if you run this command over here, LR test logi R comma logi F, if you run this, you will get the following results. So it is like this. So here you can see the chi-square test statistic is, so here your null hypothesis is the reduced model is appropriate. That means interaction term is not significant, and the alternative hypothesis is the full model is appropriate. So I'm sorry, the null hypothesis is reduced model is appropriate. That means what? Your interaction term is not significant, and the alternative hypothesis specified the full model is appropriate. That means your interaction term is significant. Okay, so based on these results, you can see the chi-square test value is 0.0661 with the p-value is very large, which is close to 1. That means null hypothesis is not rejected. So that means what? We cannot reject the null hypothesis, that is reduced model is appropriate. So based on these results, we can specify that the interaction terms are not significant for this model. Okay, so now here onwards, in order to do our analysis, we are going to use the reduced model because it is a significant model. Okay, so in order to just interpret the coefficients of logistic regression model, I am going to use this exp function. So what you need to do is, under this exp, you need to use another function which is coefficient, and here you have to specify the model name. Okay, so if you run this command, this one, sorry, oops, so exp, inside that you have to specify the function coefficient, and inside that you have to give the model name. Okay, if I do like that, and then in your output you will get the odd ratios of these coefficients, because in logistic regression model the coefficients are based on the odd ratio. So here they have given the coefficients of x1, x2 and x2. So these values are odd ratios. So in order to explain these odd ratios, the explanation is as follows. The coefficient of x1, so in this example the coefficient of x1 is about 1.06. that means what? Odds of getting level 1 of y1 is increasing by 6.41% for every additional unit increment of x1, while all other variables held constant. That is the coefficient of x1. So when you consider x2, which corresponds to level 2, it is 2.673. So that means what? Coefficient of x2 of level 2 means the odds of getting level x1 of y1 is about 2.67 times higher for level 2 in x2 compared to level 1 in x2, given that all other variables held constant. Similarly, you can explain the coefficient of x2 variable which corresponds to level 3, which is 28.97. that means what? Odds of getting level 1 of y1 is about 28.97 times higher for level 3 in x2 compared to level 1 in x2, given that other variables held constant. Okay, that's how you can interpret the coefficient in logistic regression. So now I'm going to talk about how to find the 95% confidence interval for the probability of getting 95% confidence interval in logistic regression. So in order to do that, first I need to so what I'm going to do is I'm going to get the confidence interval for probability of getting level 1 of y1 for each level of x2 when y1 is equal to mean within x2. So here I'm going to calculate the 95% confidence interval when x1 is equal to the mean within x2, because you can see this x2 has 3 levels. x2 has 3 levels. So I'm going to calculate the 95% confidence interval when x1 is equal to mean x1 within x2. So something like a group mean of x1 which corresponding to x2. Okay, so in order to do that, I'm going to use this uses tapply function. Using this tapply function, I can calculate the group mean of a continuous variable which corresponding to a categorical variable. So if you just run this command over here, this tapply function, only this one, tapply x1 comma x2 comma, if I give the function as mean, then if I run only these two commands, yeah, it should be something like this. So the problem is something like this. So here I need to give the name like this, data to new $x1, and here data to new $x2 comma mean. So I need to specify the function like this. So I need to specify the function like this, t apply data to new $x1, data to new $x2, because I didn't attach the data set. So in that case, in order to access the variable's name, you should give the dataset name like this, and then you can access the variable using this $sign. Okay, so if I run this command over here, then you can see in your output that the mean of x1 that corresponding to all levels of x2. So that means what? Here the mean of x1 when x2 is equal to level 1, and mean of x2 when mean of x1 when the level of x2 is 2, and this is the mean of x1 when level of x2 is 3. So now I'm going to predict, I'm going to calculate the 95% confidence interval when x2 is equal to either level 1, 2 or 3, and y1 is equal to the mean of x1 within x2. That means when x1 is equal to any of these three values. Okay, so in order to do that, I created this data set with these values. So if you run this this function new DA or new this object, if you run this new object, you can see now I have 3 rows. The first row is the level of x2 when it is 1, and when level of x2 is equal to 1, the value of x1 is the average value of x1 corresponding to level of x2, which is 1. Okay, and here the mean value of x1 when x2 is equal to level 2, and here the mean value of x1 when x2 is equal to level 3. So now I am going to calculate the 95% confidence intervals for these 3 observations. Okay, so in order to do that, I am going to first I need to predict. I need to use a predict function in order to calculate the standard errors which corresponding to these new observations. So in order to do that, I'm going to use this predict function. Inside that, first you need to specify the model name, and then you need to specify the object that corresponding to new observations, and here you need to give the type equals response. And here, if you since I'm going to calculate the confidence intervals, I need the standard errors as well, so you need to give this sc.fit equals true. So I'm going to run this command in order to get the confidence and standard errors and the estimates of this prediction. So if I run this one, and if I run this, if I see this object, this pre_val over here, now you can see these are the fitted values which corresponding to levels of x2, and these are the standard errors of these fitted values for each level. So now basically using this this information, you can calculate the confidence interval, because basically the formula of the confidence interval is what? It is the fitted value plus or minus the standard error of that fitted value. Okay, so in order to calculate that, I am going to use a for loop over here. So first I need to define the for loop. In my for loop I have created the two vectors. The first one vector is to store the lower limits, and the second vector to store the upper limits. Okay, so like this. So this LL is for storing the values which correspond to lower limit of the confidence interval, and this UL is corresponding to store the upper limits of the confidence interval. So I am going to iterate this 3 times because there are 3 observations. So in each iteration I am going to store the lower limit and the upper limit by just accessing the values of this pre_val. Okay, so I am going to run this loop. Then after doing that, I can access these 2 objects. So here these are the values which correspond to lower limit, and these are the values corresponding to upper limits. So this first value is the lower limit which corresponding to the level 1 of x2, and if you consider this vector upper limit or UL, the first value of that corresponding to the level 1 of x2. Okay, so likewise there are 3 observations in LL vector and the UL vector. Okay, so that's it for today, and if you need anything to know about this video, so just post a comment at the end of my video. And at the same time, if you think this video is useful to you, then just put a like on my video. And at the same time, if you want to see more videos like this in future, please subscribe my YouTube channel. Thank you. Have a nice day.